In this video, I'm going to be talking about one of our tests for convergence and divergence. This one is called the divergence test, sometimes considered or called the nth term test. Okay. This one's a nice test because it's super simple. If we're adding up an infinite number of things, and those things, those terms, if the terms as we go to infinity are not getting incredibly small, if they are not going to zero, then the series diverges. Okay, so if the limit of the nth term doesn't equal zero, then the series diverges. That's all we have to look at. So this is a good test to try first, but it does have a downside. Sort of the downside is if the limit does equal zero, that means the series has a potential to converge, but so it's an easy test because if you're looking at in our sigma notation this thing, it's been a bit since we've worked with a lot of limits, but we're going to revisit that quite a bit in this unit. But you're looking at what's happening here. So if I look at the limit of that, well, I guess k goes to infinity. Okay, we know the degree is the same on the top and the bottom, so this goes to 1/3. And as we look at these, you'll see those more readily. You're gonna go, that doesn't go to zero. This isn't zero, which means this series diverges. Okay, we'll do the same thing in this next one. This one, okay, we know from experience that exponential functions grow a lot faster than polynomials. If you weren't convinced over this, remember that if I went to infinity, we'd have infinity over infinity. So you could use L'Hopital's rule here. In one step, it'd be pretty clear that this top is growing way faster than the bottom, which means it's going to infinity, which still doesn't equal zero. So this series must diverge. Okay. This is a special series that we'll be dealing with quite a bit over this unit, but for right now, let's just look at the limit as then goes to infinity. Denominator is going to grow a lot faster, so it goes to zero, which means it has the potential to converge. It does not mean that it converges. So this is inconclusive, which means we're going to have to go to one of our many other tests, and I will show you that this series, whether the series converges or diverges through a variety of different tests. All right, this next one, we have if an is cosine of pi over n for n equals 1, 2, and so on, which of the following statements about the series must be true? Okay, well, let's start looking at the terms. That's the whole point of the divergence test, is what's happening to the terms of the series. Okay, so if I plug in 1, we'd get cosine of pi, which is -1. If I plug in 2, we get pi over 2, which is 0, cosine pi over 3, and so on. Okay, so we're going to get pi over 4, pi over 5. That's not a unit circle value, but essentially what's going to happen is this thing is going to keep going back and forth between -1 and 1. Okay, it's just going to keep bouncing. So since it keeps bouncing, this series diverges because the limit does not equal zero. We're never going to prove the series is convergent using the nth term test, whether it's convergent or divergent. And the series may diverge if the limit's zero, but that's inconclusive. So even if we didn't have the series, you could probably sort this one out. But this next problem is a pretty classic how they'll test this on the AP exam. They'll present you different series, and your job is to look at whether the series converges or diverges. We will learn many more tests, and they'll start having a variety of different types of series. But for right now, we've got our nth term test. Okay, cosine. This again is going to keep bouncing from -1 to 1. So this one diverges. Okay, this one, if I look at the limit as n goes to infinity of 1 plus 1 over n. Well, this piece here is going to go to 0. But we still have this 1. So the limit is 1, which means we're adding 1 infinitely, which means this does not equal 0. So this one also diverges. And be careful about the phrasing. Sometimes they'll ask you convergent, sometimes divergent. Look at that last one. So as we go to infinity, this again will go to 0, but we still have this n piece, which is going to go to infinity. No, you can hang on to those. Thank you. Thank you. See you tomorrow. Which means that one also diverges, so all 3 of those series diverge. Okay. So I said we'd talk about this 1 over n, also known as the harmonic series, a little bit more. So we will deal with the comparison test in more detail later on, but just in general, for the comparison test, you have a small series and a big series. And one of 2 conclusions can be made. So I'm just going to kind of draw an illustration. We've got a small series, which is going to be AK. Yes. And a big series, which we're going to call BK. And 2 conclusions can be made. If the bigger series converges, this is going to hit a limit, which means this one also has to converge because it can't go past it. And then if this one diverges, that means this one also has to go up. Again, we'll get into this with more detail, but for right now, I'm going to use the comparison test to look at the harmonic series. Okay, so the harmonic series is 1 over n. So for this test, and this is kind of just an illustration, I'm going to write out some terms of the harmonic series. So we've got 1, 1 over 2, 1 over 3, and so on. This is not geometric. There is no common ratio. The limit does go to 0, so it has the potential to converge. To carry out this test, I'm actually going to keep writing terms up to 16. Okay, so there's the first 16 terms. This continues to infinity. Then I'm going to write out the terms of this, what I'm going to call series 2 for now. Okay, so series 2 is going to start with a 1. Second term is going to be 1/2. The next 2 are going to be 1/4, and I'm lining these up with the terms of the previous one. The next 4, ending at 1/8, are going to be 1/8. And then the last 8 are all going to be 1/16. Okay, so if we look at these terms, we have same, smaller on the bottom, same, smaller on the bottom, smaller on the bottom, smaller on the bottom, and so on. So of these 2 series, this is my small series, this is my big series. Okay, Well, this second series here, I'm going to rewrite by combining the things that have the same denominator. Okay, if I add 1/4 and 1/4, I get 1/2. If I add 4 1/8, I get 1/2. If I add 8 16ths, we get 1/2. And so on. Well, the limit as we go to infinity of this for these terms is 1/2. We're adding 1/2 infinitely. So this series diverges. Okay, and we've said with the comparison test, if the small series diverges, then the big series must diverge. If this doesn't have a limit, it's going to essentially keep pushing this guy up. So our conclusion, and I will use other tests to verify this as well, but our conclusion is that the harmonic series, which looks so simple, is actually a divergent series. So that has been the nth term or divergence test and a brief look at the harmonic series.